Okay, Zhang, please start.
Okay, so today I'll be sharing about the research paper regarding protecting the users against powerful facial recognition systems. Yeah, okay, so here's the background of the research paper. So as we all know, like, because we regularly post pictures of ourselves on social media and other websites. So it's easy for people, like whether it's those good ones like those companies or those malicious ones to use our photos to train the model, which can easily like identify our face. Yeah. So the research paper proposes Fawkes, which helps individuals to protect their images against these unauthorized facial recognition models. Yeah, so it tries to.
Sorry, so would you please start with the title and authors? Yeah, so I think the other students can be more aware and understand the background. Of course, you start with the background, but you can start with the title and start with.
Okay. Yeah. So the title is Sorry, let me stop the share. Wait. Yeah. Okay. The title is protecting privacy against unauthorized deep learning models. So yeah, it's what I've described just now. Yeah.
This is a paper from U Chicago, right?
Sorry.
From the research team from U Chicago.
Yeah. U Chicago. Yeah. So
Okay.
Okay. Yeah. Then I continue. Yeah. So it tries to achieve two purposes. So one is so basically it produces significant alterations to the image feature space representations through perturbations. So it will try to perturb the image such that, you know, in the features, like when you extract the features from the face, right, you do not, you cannot classify the person to an actual person. Yeah, so it aims to provide like 95% or above protection against user recognition. Yeah. Okay, so like I've described just now, so we tend to share our photos online without unknowingly helping the third-party trackers to build their facial recognition models, which can identify our faces. So yeah, so like I said just now as well, it protects like ourselves by, so we can protect ourselves actually by using this technique to add some imperceptible perturbations to our photos before we share them on social media accounts. So of course, like when we share our photos online, we want when we add some perturbations, we still want them to look like normal. So the cloaks, which is the perturbation, should be imperceptible. Yeah, and also so when the models, let's say someone look at all your photos on social media and take your photos to train a model. So when they actually look at the next time when they actually capture your real face, they should not be able to recognize you as the person. Yeah, so that's the purpose of this research paper. Yeah. Okay, so here is an overview of what's going on. So like the original face is ourselves. So we will take a photo like another person's face that is like in terms of features is quite different from our face. So let's say we take a guy's face. So we call this target T. So this guy is T. So so we do perturbations using this guy's features, right, such that we obtain a cloak image of ourselves. So as you can see, the cloak image actually, like from the naked eye, looks around the same, but it's actually like when you actually extract the features, it actually looks more like the target T rather than yourself. So when you post these cloak images online, so let's say there's a tracker online that actually crawls your photos and then they train.
Sorry, I have a question. So
Yeah.
when you are generating the original pictures or the original portraits to the collective portraits, so you have to, this Fox is to do the perturbation based on certain model, right?
Yes, definitely.
So
yeah.
they didn't mention that the paper mentioned that what kind of model that did the perturbation based. So here on this part, it just adopt the traditional adversarial sample generation technique.
Actually, they provide the algorithm which I will describe later. Yeah.
Okay. So I just mentioned it. So these feature extractors. So I think a different model will have different feature extractor, right?
Correct. They got talk about like whether they use the same model as the one the tracker uses.
Okay.
Yeah. So the let me annotate. Yeah. So let me see. How do I draw? Okay. So here there may be a feature extractor like A. Then here when the tracker uses it, they might use B. So they might use another feature extractor. So this kind of scenario later they will describe as well. So of course the best I mean the most
way is that the both is A, right?
Yeah.
Yeah, both is A. So definitely the feature extractor of A will be influenced.
Yes. Yeah, I mean the perfect scenario is if both users
But here,
A.
I still going to raise another question.
Yeah.
Suppose this is A, right? Suppose this is A. And I suppose that these two A are actually different A. The reason is that this A may somehow adopt let's call it the A prime. So this A is somehow adopt the transfer learning, right? So even if maybe this images looks like this one there, maybe. So this one looks like a man. Of course, at the initial version, A prime will make it, suppose this is a target, right? Will actually deliver the target. But when the third party use A prime to crawl the original portrait, they will label these images as maybe a girl, maybe this called Mary or something like that. So in this case, it will, after the retraining here, because this model retraining, can't the A prime to distinguish the Mary from the Derek?
From Derek is the guy, right?
The Derek is T, the target.
There is T.
So question, let me rephrase the questions. Initially, A prime can definitely recognize Mary as the target Derek, but A prime need to do the transfer learning to retraining. And the third party also now the images, despite the start initially looks like Derek, but the label is Mary. So can't the model be retrained to make the distinction, to make a distinguishment?
Okay, I think this, right? I think wait, let me close this.
Maybe so can you answer the question? This is a yes or no question.
Yes, I agree. Yeah. So I think let me see. There's a diagram that represents let me see. Is this. I think what they're trying to do is not to label the your own. What they're trying to do is so when you have a face, when let's say your uncloaked face, right, goes into the classification. So what they're trying to do is not to classify you as who you are, but rather classify you as someone else's face which is close to
your. So when we crawl the web pages, so once it has, will it go back to this page again?
Yeah. Oh, okay.
So this is initial one. So recording after, because there's a U here, right? Anyway, the T is actually here.
Correct.
So suppose there's another classification T, and T is actually different from O. So can the model learn a new boundary? So of course, the model actually will definitely confuse about T and O, but can it be retrained back here?
I guess because training and I guess training and testing are very different, right? Because training is the label, you know that this guy is married.
Because we crawl it. So you mentioned that we crawl I'm not sure whether I understand the problem correctly. So if we crawl the images, it assumes that someone need to share their portrait on the internet. Suppose I'm sharing my portrait on my personal website, and now this people is lingering. So based on this information, now that this image are corresponding to these people, especially on the Facebook. right? So first of all, there's a personal name, there's a person name, and there's a person images, so they can make the correspondence. So when
Yeah.
they plotted whether these crawling images will have a label there.
Yeah. So if let's say your friends upload a photo with your face on it, then that will that will result in your original photo being on the internet.
Mm.
So in that
So
case,
it can also target it. It also can add a tag saying that this one is me or this
yeah,
one is Yang. So right.
yeah,
So if we have this, so now come back to the question is that whether the the third party will take whether the crowd images from the third party will be attached with identity with the person identity.
yes, it will be attached with a person's identity.
If it will be attached with a person identity,
Yeah.
even if we do the clockings in the retraining model, in the retraining stage, so we'll go back to here, the fifth slide. Right,
Yes.
you mentioned that it will have retraining. So if we do the retrainings on, the model can still distinguish, just more like adversary training, right? To defend the adversary tag.
So in that case, I think if let's say there are like a small portion of your images that are let's say later leaked online that is your original face, right? Then I think this model will be compromised.
And I think so it's more like a polluting, right? So this one is more like a polluting the training model. So if we want to pollute this model, so this model is actually the tracker model. We want to pollute the tracker model so that it make confusions. So a better way is not, and just it's not just to clock into the adversary sample generation. It's more likely to let the model recognize the run label. Suppose I provide my face, I say it is Proc DOM. So I provide this kind of information. So next time he will confuse me and Proc DOM in the future. So that's the pollution. Right.
Yeah.
I still feel I just raise these questions because you read the papers. I guess you read the paper clearly and make so many slides. So if that is a problem, so maybe can, am I wrong? So may I misunderstood some part?
But you talk about like switching the labels, right? So
so the clocking, of course, the clockings can the initial giving a model an initial bad start, a bad start point, but it cannot make sure that the model can distinguish these two images later.
Yeah. Okay. So I go move on first. Yeah. Okay. Yeah. Okay. So
by the way, sorry. So by the way, so in their papers, so one images will only be transferred with regard to one target, right?
One image to one
images will.
Correct. Yeah. So you have let's say you have like 10. You have a lot of images of target T. So that we will choose a random image from the.
But even if it is not chosen random, it applies for multiple targets. But it doesn't matter. But it's just a starting point. If the model can retrain it, the model might be able to distinguish, make a distinction. But let's see the experiment. They must provide experiment for this model. Must have provided experiment for the model. Especially, we need to retrain the model. Okay, please go on.
Okay, so this methodology. So like X is the original image, which is uncloaked. XT is the target image, so which is the guy's image. Then this is called sorry, what is this symbol called? This is gamma, right? Is it?
Delta or gamma?
Delta, yeah. Delta is the cloak computed. So it's like so you basically add the perturbation to your original image to obtain your cloaked image. Then this one is phi, right? Is it? This is, yeah. So this is the feature extractor used by the facial recognition model. So it extracts the feature from whichever face. So the phi x is the feature vector extracted from an input x. Yeah, so it basically is your basically is the features from your actual face. Yeah. Okay. So what it wants it aims to maximize, right, is the so phi x is the features from your original face. It tries to maximize the difference between that and the image that is perturbed. Yeah.
Perturbated.
So, yeah, perturbated. Sorry. Yeah, perturbated. And so this rho represents is just a threshold that is set by the user doing this perturbation. So the amount of perturbation is supposed to be less than the threshold. Yeah. So this is the ideal way of training, but due to the nature of like the T, right? Because what they are trying to do here is basically trying to make your own face look more like target T. So another way of writing this, right, is basically trying to minimize the difference between xt the phi of xt and the perturbated image. Yeah. So yeah. So this one is what I think we have discussed just now. So this originally like your own image. Let's say let's say it lands somewhere. It lands somewhere here. Then they will know that this guy is you. Yeah. Whereas for here, like let's say it lands here, then they might classify you as user B instead.
No,
So
you're classifying
yeah,
a T,
yeah,
right?
yeah.
You're classifying a T.
No. As in like if this one is the cloak one. That means your original cloak images fall under like here.
Yeah, but they're actually mapped there, right? So it's mapped to T. So the original one will be reported as T.
The original image, as in the one that means the image that is uncloaked.
These positions, okay. So
Yeah. So this one is here are the ones that you have trained to
Yes, do feel a bit weird. Why this decision boundary will be moved? Do this decision boundary disappear, right?
yeah.
So why this decision boundary will be disappear? Because decision boundary is for model, and actually the adversary generation does not change the model anymore. So why the decision boundary will be changed?
No, this just means that because
No, my question is, they only apply clocking. The object to clock is image instead of model.
yeah.
But the decision boundary is a property of a model.
Yeah.
So clocking does not change any part of the model.
Yeah.
So why the decision boundary will be changed from A to B?
The decision boundary is just to do the classification.
Yes, the classification use their own decision boundary to do the classification, and the model does not change anything. The model is the clock does not change the model. So why the decision boundary will be disappear from A?
I think does the decision boundary represent like they label by the nearest neighbor?
Hello?
Hello, yeah. I think they label it as the nearest neighbor.
Okay, the label with the nearest neighbor.
Yeah.
Neighbor.
Yeah, the decision boundary I think is just a way of like, it's like an imaginary way of.
No, decision boundary is not imaginary. It is real.
Okay.
That's what Shanning's work is trying to visualize it. The decision boundary is real. Okay, maybe we can just leave it open and Zhang Cheng, you know that you have 2 reviewers to go, right? This one you'll be the reviewer to review this paper, and also you should be also review the paper presented last yeah. Okay, please go on. I find this paper has a lot of problems. So if I'm the reviewer, I'm going to raise a lot of questions. Okay, please go on.
Yeah, so how they select the target T is basically they use a publicly available data set with different labels like Bob, Carl, Diana. So they will randomly pick K candidate target classes. Then they will calculate the centroid of each of the feature space of each class. Then they will calculate your own centroid for your feature space. Then they will choose the class T based on the centroid that is the furthest away from your own centroid. So basically, it's the most dissimilar phase. Yeah. Then so now you have picked the target T. Then so for each of your image that you want to clock it, so you randomly pick a image from the target set, so XT, and then you clock it. Then you use the algorithm just now to clock it. Yeah. Then they use the DSSIM to calculate the perturbation. Yeah.
Okay, please go on.
Yeah. Then so after you have, so it's actually quite simple. So after you have done that for each and every one of your own image, then you upload these images to whichever social media accounts that you have. So basically all the photos that you have uploaded are technically they are cloaked already. Yeah, so there's a limitation here, which is like images that appear on other people's accounts that might contain your face and your label. So that one, right? That one they actually also talk about like some of the countermeasures later on. Yeah. So then they do the experiment, right? So they use 2 main data sets. So one is VGG phase 2 and the other one is web phase. So both contain like a lot of images and different subjects. And then they use these 2 model architectures. So so they have 2 models and 2 data sets. So they will actually have 4 different feature extractors based on. So basically, they will use data set A as the data set and model A as to extract the features from data set A to do the training. So there will be one model. So in total there will be 4 because you will just have 2 times 2 lah. Yeah. So yeah, so for the tracker model, right? Actually they talk about this concept called the transfer learning, in which like you might, because the actual let's say the actual data set of faces you have in, let's say in your like let's say in your country or city, right, it's not the same as those in the data set. So we assume like the tracker is like let's say a government, so they will have their own data set of people and their the images of people and their labels. So then they will use they will attach a softmax layer at the end of the feature extractor to classify the the trained images based on their own data set. So they use two other so-called like extra data sets to represent their own, their own personal image data sets. So it's Park Fig and Face Scrub. So imagine like these two are your own data sets that represent the faces of real people that you know. Yeah. So so after training these models, so then they will do the experiment. So the experiment will involve so this part actually they talk about like choosing the user U randomly from the, let me see. Okay, so the U will be from the tracker model because U represents someone that is in real life. So it must be in the tracker model. Because like we've described just now, tracker model represents the images that are like the real people of real people. Yeah. So however, to do the perturbation, right, they choose the T from the VGG phase 2 and web phase, which are not from the tracker model. So I think this is to ensure that so I think this actually kind of answers the question just now with regards to the boundaries, because like because if the target the target that you try to achieve is not in the original in the original model, then I guess it's more efficient, like it's more of a, how to say, like basically
Should be in the model, right?
yeah
T should be in the model, but you mentioned that the T is not in the model in the experiment. I'm quite confused about either your slides or the paper. But actually, this paper is published in a very well-known venue.
choose a user.
USENIX. It is published in USENIX.
I think this part, it means like because they have the decision boundary based on the your own data set. So T might not be so some part, let's say like T might not be of the actual T, let's say.
No, the decision boundary here. So they are using neural network model, right?
Yeah, neural network.
So it is neural model. The decision boundary of neural model is not based on the samples. It is based on the model. So the model tries to learn an intermediate representation or the representation vectors for an image, for each image. And so they project the image into a dimensional space. So the boundaries for dimensional space. In this space, it can using some way to do the classification. Right. So I think the boundary is not for samples or not for images. The boundary is for the model.
Yeah. Boundaries are for the model. Okay. Okay, I kind of get what you're trying to say. Yeah. So yeah, then they then cloak the images of you, and then they evaluate the performance using under 3 scenarios. Yeah. So these are the 4 so this, sorry, let me see. Let me annotate. So this one are the 4 models lah, so called, because they use the different architecture for each of the data set to train. Yeah. Okay, then I'll move on. So for scenario 1, which is the U and the tracker model share the same feature extractor. So in this case, I think they drew a graph so the x-axis represents the perturbation budget, which is the threshold, which is the rho. So of course, when the threshold increases, that means like more perturbation can be added to the image. So definitely the protection success rate, which will definitely increase. So 1 represents 100%. That means like all your images.
So in a way, so this means the successful rate is very high. Okay, please go on.
So, yeah. So they used PCA to visualize the features extracted from the faces. So before the cloaking, right? So the yellow part represents your own image. Then the gray one is just other people's images, and the red one is the target. So so after the cloaking, right, then they will basically.
Actually, so you can just skip this one. Okay, I understand that after the birth rate sample generations, the PCA will not work anymore, will not make a distinguishment. But the problem is that after what if we do the retraining?
Yeah.
Right. What if we do the retraining where the model be capable of recognize the birth rate sample?
But for retraining to happen, right, you need the new your face with the new labels, right?
Yes. So here I'm still asking the problem of the scenario of the problem. So suppose we crawl it on. So we still have the problem. So if our model on the images is used for training, so I think adding some adversary samples may not work that effectively. Of course, the best star may influence the neural network trainings. Suppose it is used for the user profile, the crawlers is going to crawl the user profile from the internet. In any way, giving images will attach a label. And despite this model adds some perturbation so that it will be recognized as another star or some target. But after it retrain the models, the model becomes robust again. So the only problem, the only explanation I can think of is that the model has already taken some of my real images or portraits for training. Then, in other cases, I add my portrait with some adversary samples. So the model will be attacked on the runtime. The model does not have the chance to retrain it. So the model will recognize the users as a target. So that would make sense.
Yeah.
As long as the model will be retrained, it will still have some chances that the model will be recognize images.
I think what you said can't really be achieved in real life, because let's say like you walk into like a place where there's a security camera that captures your face. So in that case, you can't really, adversely.
Yeah, I agree. So still question the motivation of these papers. So if it is used for retraining, it does not pollute anymore, because the model can, with correct label, the model can learn a new presentation and change its weights, so that this approach does not work. So the only problem is that you just providing the label, you're providing the wrong label, so that you provide a model with polluted or noise data. So when they retrain it, then it will make a difference. Or another argument I can think about it. I can think of it is that if the neural model, because the neural network model is not a convex. If it is not convex, so giving a bad start makes the training process harder. You get that point? So if you're getting a very bad starting point, so the network is doing optimization, doing the search. So the search process may not be so smooth, may not be so good. So let's look at the experiment. So my laptop may have only 20 minutes to go. Maybe you can finish within 50 minutes.
Yeah.
So continue.
Please.
Yeah, then for scenario 2, which is, let me go back. The U and the tracker model have different feature extractors. So they use the different the model, we call this a model, yeah, to extract the features. Then yeah, then the you can see like it's like the blue color part is actually still quite near to the yellow color part instead of being near the red color part, because they use different models to get the features. Yeah, so but then so to solve this problem, they actually propose to use a more robust feature extractor. Yeah, so as you can see, after using the more robust ones, right, the blue color one actually nearer to the intended the intended space. Yeah. So then they talk about like how to generate the robust model. So so they talk about like the ability for feature extractor to be more robust, right, is done by applying adversarial training when you actually train the model.
Yeah, those are training is so important, and then it's even worse. They can train according to the adversary sample.
Yeah.
So it makes the model even better to
Yeah. So that's how they did it. Yeah. So they first generate the adversarial examples of like certain images using the PGD attack. So then they train each feature extractor using these adversarial examples. So then the updated feature extractors are then used to generate the cloaks on the data set. So in this case, it will be more robust. Yeah. Yeah, so actually they did so this is the overall experiment. So on the vertical axis is the U feature extractor, and this horizontal one are the feature model extractors. Sorry, the tracker model feature extractors. Yeah. So yeah, so you can see it's actually for the robust model is actually quite successful. So 100% represents that basically all the images they classify are actually classified wrongly. Yeah.
classified wrongly.
Yeah.
Means the attack is successful.
Yeah, it's successful. Yeah.
Against the robust against the model with the adversary training.
Yeah, so the model has to be trained using adversarial samples.
Here's a contradiction.
Yeah.
In the contradictions, the model becomes even robust. But
Okay, the model I am talking about here is the one you use to generate your so it's talking about this one, yeah.
So you are trying to attack the model with the adversary training model. Okay, I see.
Yeah, so it's this part. It's not, this one is used by the tracker model. Okay. So tracker model is like the bad guy, let's just say. Okay. Yeah. So you're trying to improve this like your own model. Yeah. Yeah, okay. So scenario 3 uses the web okay, scenario 3 I'm not too sure how they train the tracker model, but they talk about like the tracker model uses the web face data set to train their own model from scratch. Then they say that the success rate is 100% as well.
Okay.
Yeah. And then so that's the personal experiments using the model. So they actually use the real world face recognition APIs for testing also. So these three, so there's Microsoft, Amazon, and Face++. So Face++ is, I think, it's a China face search API model.
So they did like 3 experiments. So one is without protection. So without protection means like you simply just upload your original image and see whether it manages to locate that it is you. So all 3 gives 0%, which means that all 3 of them are actually quite strong in a sense. Yeah, and then for normal cloak, which is the one basically you generate your own model without the adversarial samples. It's actually the quite bad for Amazon and Face++.
I have a question here. So given that it's face recognition API, so it is somehow is a black box model, right?
Yes,
so
you don't really know the
if it is not provided service, it is just provided yes or no. How can they learn the adversary sample generation, the adversary samples?
How can they?
You can see if we want to do the adversary sample generation, it must be given the gradients for us to apply a tag, right? So if it is, I'm not sure whether API can reply a yes or no answer or a confidence score. If it provided confidence score, it was still likely for us to apply the tag, right? Right. So this is my first question. So I assume that it's providing a similarity or a confidence score. This is the first my question. The second question is that, say a text model, they're not sure this API is retrained, right?
Yes, they don't know whether it's retrained.
It is not retrained. It's more likely to adopt some Siamese model to recognize whether two faces are similar. So in this case, definitely doing adversary sample generation will be effective, but it's not the story is introduced in the overview part, right? Okay.
Yeah. So of course,
I'm the reviewer probably will reject this paper. Okay, please go on.
Yeah, I think that's the last slide.
That's all, right?
Yeah, that's all. Yeah.
Okay, I think this paper is kind of straightforward, and thanks Zhang for his report. I think he goes through the paper thoroughly and clarifies, I think, almost all the details. You grasp the high-level structures. I think Zhang's report is always good. But I hope that your progress can be as good as your report.
Yeah, okay. So actually, I was about to share my progress as well.
Okay, so if you share progress, I'm going to stop the
stop first. Okay. Yeah.